In this video, we begin our discussion of molecular structure with diatomic molecules. We start with the simplest diatomic molecule, our spherical cow, H2+. This is a three-particle system which consists of two hydrogen nuclei and an electron. Now, as we noted with the multi-electron systems, any three-particle system, the Schrödinger equation is unsolvable. So we are going to have to make some approximations in order to solve for these problems. The approximation we will use is called the Born-Oppenheimer approximation, named after Max Born, he of the Born interpretation of quantum mechanics, and J. Robert Oppenheimer, he who was the director of the Manhattan Project during World War II. In the Born-Oppenheimer approximation, we first note that because nuclei are much more massive than electrons, that their motion is much slower. As a result of that, in our approximation, we can separate nuclear and electronic motion, and that means that we can separate the wave function into a product of a nuclear term and an electronic term. We're going to be focusing on the electronic term since as chemists at this point we're most interested in the electronic characteristics of the molecule. So we will write the Schrödinger equation with an electronic Hamiltonian that ignores the nuclear kinetic energy, again because the nuclei are moving so slowly. And what we will do is we will solve the equation for specific internuclear separation. Here we see the equation with the terms for the kinetic energy of the electron, the attraction of the electron to nucleus A and nucleus B, and the final term represents the repulsion between the two nuclei. In this equation, we're going to set the nuclear separation at a particular value of R, solve the equation to find the electronic energy, which is E electronic, for that separation R, and then we will set a new separation R, solve the equation again. So we will get the electronic energy as a function of R, the distance separating the two nuclei. When we plot the electronic energy as a function of the internuclear separation R, and that's what we're talking about here, the distance between the nuclei, we see the intramolecular potential that you have seen many times before. In this case, we have a potential well. Now, we'll see later that we don't always get a potential well. We'll talk about the significance of that. But this is the basic idea. This is a solution, the electronic energy that we get when we solve the electronic Schrödinger equation as a function of that internuclear separation. What about the nuclear component of the wave function? Well, again, we're not going to be terribly concerned about that right now, but this equation shows the Schrödinger equation for the nuclear component, and the energy here is the total energy of the molecule. The Hamiltonian shown here gives us the kinetic energy for nucleus A, the kinetic energy for nucleus B, and then the electronic energy that we got from solving the electronic Schrödinger equation. Alright, so we're going to focus now on the electronic wave function. And we're going to use something called LCAO-MO theory, which simply means a linear combination of atomic orbitals to form molecular orbitals. We're going to retain that entire concept of orbitals in our discussion of molecular structure, and to generate these orbitals, we're going to take linear combinations of atomic orbitals. This makes intuitive sense to those of us chemists simply because we've always considered the interaction between atoms to involve orbital overlap, so that we're going to form molecular orbitals by taking combinations of the atomic orbitals of the constituent atoms in the molecule. Okay, so here we see the form of the molecular orbitals and what we mean by a linear combination of atomic orbital. The wave function representing the molecular orbital is seen here, and very simply what we're going to do is we're going to take the 1s orbital on hydrogen A and the 1s orbital on hydrogen B, and we're going to add those together. The coefficients in front of those two are going to be our variables. Now, in this particular case, since the two hydrogens are equivalent, we're going to have two possible results from this linear combination, one in which the coefficients are equal to each other, and we're going to learn that that's called a bonding orbital, and we'll find out why a little bit later, and one in which the coefficients are of equal magnitude but opposite signs, and that's going to be something called an antibonding orbital. So we're going to get two molecular orbitals from this linear combination, and that in general is what we're going to find. The number of atomic orbitals that we put into a computation is going to be equal to the number of molecular orbitals we get out. So again, just to reiterate, the number of atomic orbitals in this case that we're using in a linear combination is 2, the 1s orbital on hydrogen A and the 1s orbital on hydrogen B, and we're going to get two molecular orbitals out, one in which the coefficients are the same, and one in which the coefficients have the same magnitude but opposite signs. Okay, now here are the graphs of these two molecular orbitals that we generated. The graph at the top shows the linear combination of the 1s orbitals where the coefficient is the same, and the graph here shows a linear combination where they have opposite signs. Now we have labels for these, and the labeling actually depends on the textbook. You'll find different books label these differently. Our textbook refers to the one at the top as a 1 sigma G, and these are called sigma molecular orbitals, and we'll talk a little bit more about what that means later on. And the one at the bottom is a sigma star, 1 sigma star labeling. They also have subscripts, and we'll note that what we were currently referring to as our bonding orbital has a subscript G. The G stands for Gerada, which means that the molecule is symmetric, or the wave function is symmetric with respect to inversion. So we have this subscript Gerada. Symmetric with respect to inversion means that if we look at the wave function on one side of the origin and change the coordinates from x, y, z to negative x, y, z, that is called an inversion operation. And when we change those coordinates, and that's represented by this arrow here, we go from one side of the molecule to the other side of the molecule. If the wave function has the same sign on both sides, it's referred to as Gerada. Now, this particular symbol, or this particular way of labeling the orbital, is only used for homonuclear diatomics. We will not use this for heteronuclear molecules. In this case, we see the bonding orbital does not change sign, so it's G. The antibonding orbital, on the other hand, is labeled U, and that means ungerada, which means it's antisymmetric, which, as you probably would suspect, means that it does change sign. And if it does change sign, we'll see here from this arrow, it goes from a negative sign to a plus sign. The wave function changes sign. That makes it ungerada. Now we're going to look at the probability density associated with these molecular orbitals, and we'll get a better understanding as to why we refer to one orbital as a bonding orbital and the other orbital as an antibonding orbital. So here we have the probability density of the Gerada orbital, and we'll note that when we take it and multiply it out, simple multiplication here, this is what we get, 1SHA squared plus 1SHB squared plus this 2 1SHA HB. We do the same thing for the ungerada orbital, and we find that we get a similar result, but in this case we have this negative term here as opposed to the positive term in the psi G probability density. Now here's the key. The positive term in the upper equation represents a constructive interference, which means we get a buildup of electron density in the region between the nuclei. And we'll see that on a slide in a moment which shows the graphs of the probability density. So there's enhanced electron density in the internuclear region. We'll also note that the resulting wave function gives us a shrinkage of the orbitals in the vicinity of the nucleus, all of which lower the energy of the molecular orbital. And we'll note that this orbital has lower energy than the atomic orbitals. Because it's lower energy, it's more stable than the atomic orbitals, we refer to it as a bonding orbital. It stabilizes the bond. On the other hand, we have this situation where this negative term results in a destructive interference and a decrease of electron density in the internuclear region, which yields an orbital which is higher energy than the atomic orbital, and because it's higher energy than the atomic orbital, it destabilizes the bond, and we refer to that as antibonding. Here are the plots of the probability density. We have the bonding orbital above, where we see in that region between the nuclei a buildup of electron density from constructive interference, and then the antibonding orbital, which has destructive interference, and in fact at the very center point between the two nuclei we have a node where there's zero probability of finding electrons. Here are the electronic energies associated with these two orbitals. We'll note the bonding orbital has our familiar potential well that we've discussed before, which indicates a stable bond, but the antibonding orbital has no well. It is sometimes referred to as a repulsive potential and is less stable than the atomic orbitals themselves. So the antibonding orbital actually is a destabilizing factor in the molecule. Here are some results from the calculations for H2+, and again this is H2+ with only one electron, using the simple sum of the 1s orbitals. It gives us a bond length of 130 picometers, and this compares with the experimental value 106, so it's quite far off. The dissociation energy is also much lower than the dissociation energy from the experimental values. If, as we did with helium, we replace the atomic number Z with Z effective, we find that Z effective gives us a value of 1.24. Why is it greater than 1? I'll let you think about that. And that a bond length of 106, which is right on the mark. The dissociation energy is better than what we got without using the Z effective. However, it's still significantly off. So that's H2+, and that's our simplest situation. That's our spherical cow for molecular structure. We've started our this concept of constructing molecular orbitals by taking linear combinations of atomic orbitals. In the next video, we'll look at this molecular orbital theory in much more detail with various homonuclear diatomics.